All right, so last class we stopped right here. We were discussing about 3D representation of the forces, moments, etc. So in 3D problem like this, when we start solving these problems, it's better to represent all the forces and moments acting on different parts through a vector form. Okay, so let's read the problem here. Can you hear me clearly?
Yes, doctor.
Okay, very good. So in this figure, what do we have here? Shows a crank loaded. So this is the crank. It is loaded with a force of 300-pound force that causes twisting and bending of a 3/4 inch shaft. The shaft is AB here. And it is fixed to the support at the origin of the reference system. So this is the origin. You can see here the y-axis, the z-axis, and the x-axis. So it is fixed right here. In actuality, the support may be an inertia that we wish to rotate, but for the purposes of stress analysis, we can consider this as a statics problem. So basically, what we are saying is when you apply this force due to inertia, there will be some twist happening on the shaft, but we cannot do dynamic analysis. So in design, what we do, we approximate this problem as a static problem by fixing this other end. Draw a separate free body diagram of the shaft AB and the arm BC. You can see that there is some difference in the cross section. The arm BC is rectangular in cross section, the shaft AB is circular. Compute the values of the forces, moments, and torques that act on each of these components. Label the directions of the coordinate axis on these diagrams. Compute the maximum torsional and bending stress in the arm BC. Locate the stress element on the top surface of the shaft at A. So basically here. And calculate the stress components that act upon the element. Determine the maximum normal and shear stresses at point A. Okay. So where do we start? So we have to find the stress at point A on the shaft AB. We also need to find where the stress is maximum for the link BC here. Not a link, it is a, let's say, arm BC. Okay. So how do we proceed? First, we have to draw the free body diagram, but even before that, let's figure out what are the forces acting. So due to the external forces are F here, this force F leads to a force and a moment at point C, if you replace at the point C. Okay. In the same way, at the point A here, you will have force and couple of moments. So this is why we need to represent everything by vector quantity. So first let's draw free body diagram. Let's say for BC. Okay. Just going to represent it as a rectangular bar. You have a cross section. Okay. Although it is thin, maybe represent it as thin bar. Okay. BC. We have a force here, so we need to first figure out what are the forces and moments acting at point C. We can consider end B as fixed. Since the end A is fixed, we know that no rotation, no displacement, etc. In the same way, we can consider B. Once equilibrium has reached, this end is fixed. Okay, so before we find what kind of reactions are there at point C, we need to figure out what are the forces. So first, represent the force, write the force here. We have F equal to 300 pound force in the negative y direction. So write it in vector form. Since it is negative in the negative y direction, you can write minus 300 and 0. So this is the force vector. Now we will also need the location where the force is acting. Okay, it's important to have this location. So first we know that A is the origin. So if we look at the location, the x component is going to be 5 inches in the x direction plus 1.5 inches here. So R for the force F 6.5 inches. 5 plus 1.5 6.5. Let's see the y component. The y component, we can imagine it as 0 here. And the z component is negative. So the y component is necessarily 0 because it is in the xz plane. Let's get the z component. We have minus 4 inches. It is right at minus 4. Okay. So this is the, with respect to origin, this is the position vector for the force F. But we need the position vector of the point C as well, because we want to get what are the resultant moments acting at point C as well, not only at point A, point C as well. So let's get the relative position vector. So to get the relative position vector, first I get the position vector of the point C. So we can see here 5 is x, y is 0, and we can imagine C is minus 4. 5, 0, minus 4. Okay. So we can get now the relative position vector F with respect to point C will be RF minus RC. So which would be 1.5, 0, 0. Okay, so now to figure out what is the force acting at point C and the moment acting at point C, we can clearly see the force acting at point C will be the same force F. We replace it with a force and a moment. To get the moment, so in this case it comes out very simple, but it's better to write it in vector form. What is the formula? Cross product between R and F. Okay, So this we can write it in the determinant form. I, j, k. The R value is 1.500 and the F value is 0 minus 300 0. So we can eliminate the first column and the second row. Let's see here, what do we get? Clearly we can see it has to be with respect to z-axis. Okay, so it is better to eliminate the second column and the last row. If you do that, we get 0, 1.5k, and we have to use the expansion. For the expansion, we have to put plus, minus, plus, and then we get a minus here. Okay. So minus of minus is plus 300 times 0 minus 1.5k. Finally, we get a minus. We get minus 450k. So this is the moment acting at the point C. So and it is with respect to z-axis. So let's note down the axis here. This is the z-axis and y-axis. Going up is the y-axis. The z-axis in the other direction. This is the z-axis and the x-axis. Yes, in this direction. Okay. So the moment is about negative z-axis here. So it leads to a torque for the BC. So if you use your right hand rule, this will be the torque MC. In other words, torque also can be represented in this direction with a double arrow. So this is the free body diagram. The end B is fixed. So it is not going to allow torque. It is not going to allow any XYZ displacement, and also no moments. Okay, so no rotations. So there are moment reactions here. So you will have all the three moment reactions and all the three displacement. Because of displacement, you have force reactions. Okay. So we will have around 6 different reactions here. Reaction forces here at the point B. But since we have only the torque here, so there is a torque reaction, and since we have only this vertical force, there is a reaction in the vertical direction. So we can see only the Y reaction force, and there is a torque reaction. Otherwise, with a double arrow here. Let's call this torque C. Okay, so this is the free body diagram for arm BC. Let's go for the free body diagram for shaft AB. So AB is along X direction. Draw the shaft. X, Y, and then we have Z direction coming out of the board. So now we can think of the force F acting at the point B. The same force F is acting at point B as well. But for finding the moments, here we have to use R cross F. You have to replace the force with the force and moments at point B. So since we need at the point B, we have the location position vector for the point force F, but for point B, we need to write what is the position vector before we proceed. So let's first write what is the position vector for point B. The X value is 0, the Y value is 0, sorry, the X value is not 0, the X value is 5, Y value is 0, and the Z value is 0. So X is equal to 5, Y is 0, Z is 0. So now with respect to B, I need to get the location of the force F. So what do we get? We have 5, 0, 0 here. Here we have 6.5, 0, minus 4. Okay, 0.5, 0, 6.5 minus 5. Will be 1.5, 0, and minus 4. So this is what we get. Now let's go here. Moment at point B will be R, F, R, position vector of F with respect to B. Because we are doing with respect to B here. Cross with F. Okay. So let's write the components. 1.5, 0, minus 4, and then we have the force components 0, minus 300, 0. So we will get the results here. Take the last row in the second column, eliminate. Yeah, plus, minus, plus, and minus. So minus of minus 300 becomes plus 300. Then we have minus 4i minus 1.5k. Can replace. Minus 1200i. So I can write it in vector form, the array form. Y component is 0. Then we have minus 450. So at the point B, we have moment about the x-axis, and it is about negative x-axis 1200. Use your right hand rule and you will realize in what direction it is. So this is a torque. This is essentially a torque for the shaft. So now we need to draw the free body diagram. Let's go up here. Okay. Torque about negative x-axis. I'm going to represent with double arrow 1200. Then there is a moment about z-axis. The z-axis is coming out of the board towards your face, and it is about negative z-axis. So your moment is going to be like this. Torque B is equal to this. Moment B on the other hand is 450. So just in case, if you want to put a negative signs, you can put to show that it is in the negative z direction or negative x direction. Okay, so we have F, torque, and bending moment. Now the point A here is in the top. So essentially our point is in this location. Okay. Okay, so what are the stresses? First we are draw a separate free body diagram. We have done that almost. We have reaction here. So the reaction at A so right at point A, we need not find the reaction forces, but just in case you want to represent the reaction forces, those will be RA in the y direction. Since we have a torque, we have a reaction torque with a double arrow on the other side, torque A, and then bending moment will give rise to bending moment reaction at A. So we are done with the free body diagrams. You are asked to compute the maximum of the torsional stress and the bending stress in the arm BC and indicate where these act. Let's go back to BC here. We have basically a torque here. Okay, so since we have a torque reaction, So let me just get rid of this, just to avoid confusion between torque and bending moment. So what we have is a torque. Torque will give rise to shear stresses. And the shear stress just depends upon the from the centroidal axis, the radial distance or height here. In the case of a rectangular cross section, it will just depend upon the cross section dimensions. Does not depend upon the length. So the torque stress, shear stress from torsion does not vary along the length. However, the bending moment varies along the length, and it will be maximum at this end B. So the location B will be the point where your stresses are maximum. So we can write the equation by the side here. So we have the torque value 450 K and the F value 300. Yeah. Okay. So for a rectangular cross section, we have a formula here. This is the formula we need to work with. Let's see the cross section dimensions. We have 1/4 and 5/4. Okay, so the dimensions of the rectangular cross section. If I were to draw, one by 4. These are the dimensions, and the axis will be Y and X. X direction. If I look at the cross section from this side, this is the X direction in this direction and Y. And the Z axis is going inside. So the torque is with respect to the Z axis, and we can see here the direction of the torque. Is like this on the cross section. Okay, so let's go back to the formula here. The largest side is B. So first we find B over C ratio. Five by 4 or 1/4 equal to 5. So let's see here, if we don't have a value 5 here, so we have to interpolate between these two quantities to get your alpha. We just want the maximum shear stress. So we will, instead of, let's see here, we can use the quantity alpha here, or we can use this formula. Let's use this formula. Tau max, we get T over BC square. So T is nothing but, we can use the magnitude BC square 5 over 4 1 over 4 square multiplied by 3 plus 1 over 1.8 over B over C. so which is nothing but 5. So this is the shear stress. But which component of shear stress? That also we need to see. Since we are taking the longer side, most probably the points of interest could be here or here. So one of these points. And in these points, the component is specifically going to be tau z. Since this area is perpendicular to z direction, the first subscript will be z, and the second subscript, most probably it's going to be the x direction. So this component we are calculating is zx. So this is also what in the question, if you see, we are asked to figure out which component it is. Let's see, where did we read? Indicate where they act. Okay, so where these act, probably in these 2 points, and this is the component of the shear stress. So let's calculate this. So 16 times 4, 64, 5 over 64. I'm going to directly write the result, 5 over 64, and multiply by 3. 3 plus 1.845. So we get in pounds per square inch, or if we use kpsi, it will become 19.354. Okay, so this is the result we get, tau max value or tau zx value. Bending stress, so that is remaining. We have bending stress for BC. The bending stress will be along the z direction, so sigma zz. Definitely this is a sigma zz component, and it will be maximum at the end B. Here we need the length. The length is 4 inches. We can assume this is 4 inches. So the bending moment will be F times 4, which is 300 times 4. I will be BD cube over 12. So if you look at the cross section, this is BD cube. Cube over 12. So 1 over 12 times y, the distance from the neutral axis, which will be half of the distance of 5 over 4. So 5 over 4 and half of it. we can evaluate the maximum bending moment at the top surface. So the maximum bending moment at point B on the top surface can be compressive on the it is a tensile on the top and compressive on the bottom. So we can have plus or minus sign here if you want, but let's calculate this. Stress. So this is normal stress for BC. To 100 divided by 1/4 times 5/4 square times 1/12, that is divided by 12, then multiply so we get 18.432 kpsi. So these are the stresses. Let's go back and see if our solutions are right. So 18.4 kpsi sigma and the tau value 19.4. So exactly what we get. It's very simple. Once you represent in vector form, you won't miss anything. If you don't write it in vector form, there is a possibility that you will miss one of the vectors here and there, especially with respect to the moments. So you will definitely miss moment values. So be careful there. So let's calculate.
Doctor,
Yes. What's your question?
we won't use the formula VQ over I.
Over here. That's a good question. Let's see here. If you can see here, this is a rectangular cross section, and since we have a torque, whatever transverse shear stress we have on the arm BC here, it will not be significant. So usually, if you have torque, you will neglect calculations for transverse shear stress, VQ over IB. Okay. In case you don't have any torque, then you have to calculate VQ over I. Is that clear?
Yes, thank you, Doctor.
Yeah. So usually we neglect that. So let's go for part C here. In what's part C? Locate the stress element on the top. So we are asked to locate this stress element here. And then identify all the stress components, calculate all of them, all of the stress components. So let's go here. Okay, so what are the different forces we have? The transverse shear stress. Sorry, transverse shear stress is there. The bending moment is there. But since the torque is there, we can forget about transverse shear stress. Torque will take care of the shear stress calculation, and then bending moment. The bending moment will give rise to normal stress. But when you look at here, it is not only the MB value which give rise to the normal stress at this point. F also gives rise to another bending moment value, F times the distance. So let's see the distance here, 5 inches. So 5 times F is one bending moment contribution. And also we have this bending moment contribution. Okay. So there are two bending moment contributions. We need to add them together at the point A. Okay. We can forget about transverse shear stress. Then we have the torque value. So let's go here. Write down the bending moment at A. Now the bending moment is with respect to the Z axis. We can clearly see that it is negative. All the quantities are negative with respect to Z axis. So I'm going to write Z in the top. And minus 450, we get minus F 300 times 5 gives rise to 1500 minus 1950. So this is the bending moment we need to consider. And the torque value. Torque at A. Again, the see here. I think it is not with respect to Z axis. Sorry. I may have missed something. Let's be sure. Yes, it is with respect to Z axis. Absolutely correct. So this is with respect to Z axis. Let's take the torque value. Torque will be with respect to X axis. And the torque value is with respect to negative X axis, or yes, it is negative X axis, and therefore minus 1200. So now let's calculate what is the component of normal stress from bending moment. If you look at the normal stress due to the bending moment, it is definitely with sigma xx component. So m over I times y, we have 1950. Now we need to figure out whether the stress is positive or negative at point A. If you take the point A here, since it is with respect to negative Z axis, at point A, the stress component is definitely tensile, so positive. So we'll just take it as the positive quantity. 1950 pi over 64, the diameter power 4, or we given the diameter 3/4 of an inch. And here we'll have half of 3/4 inch. So now we can calculate sigma xx. For AB. We have pi over 64 multiplied by 3/4 cube. Okay, so we get 47.082. Okay, this is the sigma xx value, and we can also calculate tau. Now we need to figure out what component it is. Since this is the shear stress due to torque at the point A, we need to draw the cross section. So draw the cross section over here. We draw the cross section perpendicular to x-axis, and then vertically we have y. And here in this direction we have z. Let me go to the 3D diagram. Yes, z. The point A is right here at the top. So we can clearly see the component is, since it is on a plane perpendicular to x-axis, first subscript is x. At point A it is in the z direction. So xz component. The radius or the diameter divided by 2 here. The torque value is known, 1200. Now we need to be careful about the signs for shear stress. In the previous one also we needed to be careful. The torque is in the negative z direction. So where is the z-axis on the, sorry, negative x direction? Where is the x-axis? X-axis is coming out of the board. So the torque is going this way. So which means your tau xz component is in this direction, opposite to z direction. And we need to draw the stress element at the point A to exactly figure out whether it is positive or negative. So we look at from the top here. And we have the stress element like this. Since the torque is in the negative x direction, we have like this. On this surface, it is like this. Okay, so we need to draw very carefully the stress elements in 3D to figure it out. Since it is in the xz plane, I have to draw my stress element in the same xz plane. When I draw that, this is the stress element. This is the x and the z plane. The x and the z. All right. Now, obviously, my sigma xx is positive, tensile. So I can write it, no problem here. But what is the direction here? On the surface on the right here, my clockwise rotation leads to the negative z direction on the surface at x. So this fixes all the other directions. And now I need to figure out whether my tau xz is positive or negative. From the stress element here, the same rule applies. Pick anything, any normal. And this is positive. But you look at the direction of tau xz, it is negative. So they are of opposite signs. Therefore, your shear stress is negative. So be careful here in determining the whether a shear stress is positive or negative. Okay, so now let's go for the values. 1200. We have pi over 32 d power 4 into 3 over 4 divided by 2. So we will get a negative value. Let's calculate that. We get 14.4866. Okay, so let's check the calculations if they are right. Go to C. We get negative 14.5 and 47.08. Okay, the previous case, I think we did not take care of the sign of the stress, shear stress in particular. So we selected a point on the top. Since we have the torque in the negative z direction, any point here, okay, so here it is in the positive x direction. We can see if we create an element in 3D at the point B, we are going to create an element like this. Specifically an element here. Why is this not drawing? It's drawing somewhere else. Okay, an element like this on specifically on which plane? XZ plane. That will be the stress element. We have ZX here, ZZ, so it will be on XZ plane. So if I draw the stress element here, the x-axis is going down, Z on the left. Z is on the left hand side. And when I apply a torque using the right hand rule system, right at this point you can see the direction on this plane. It is in the direction here. So which means on this plane, are we right? Okay, in this direction. So in this case as well, it looks like it is negative. Okay, especially if it is taken on the points on the top. definitely the shear stress appears to be negative here as well. Okay. But sigma ZZ is positive. So we have identified all these stress components and the values. And finally, determine the maximum normal and shear stresses at point A. That will involve Mohr circle, maximum normal stress. So just use the formula. We have calculated all the values. Just use this formula and evaluate what are the principal stresses. That's about it. So that will be your maximum normal stress and maximum shear stress. So this is very simple. I'm not going to do that. You can do it by yourself. Calculate using the formulas or using Mohr circle method. What are the principal stresses and the maximum shear stress. Okay. Now, since we have only two components, it is 2D problem, reduces to a 2D problem. You can easily solve it. Okay. All right. Now this problem also I have completed. So I'm not going to solve this problem again. For circular or square cross section, it is completed. Next class, we will continue with formulas for thin wall tubes, and we will complete this chapter and move on to a new chapter. Okay. So see you guys. I will meet you again on Tuesday. Any doubts? If you don't have any doubt, I'm going to stop here.